Thanks, Sam. Yep, I'm excited to get started today with our first talk, which is going to be a really fun one. Dave MacQueen is joining us remotely from approximately the other side of the world to tell us about successor ML.
Okay, can you hear me?
Yes, we can hear you.
Not too much echo? Hello?
You sound good to me.
Okay, here we go. So I'm Dave McQueen coming to you from the Oregon coast, and I want to talk about a proposal for successor ML, which I've called um, MsML, which roughly stands for McQueen's own version of successor ML, which is a historical illusion, if anybody gets that. Okay. So, what is it about? Well, uh, one moment. Let me see if I can find myself again. Right, there we are. So, as I said, it's McQueen's own version of successor ML. It's defined in the document that I wrote up a while ago, which is indicated at the bottom of this slide. And I'll put that up again at the end of the talk. And it's mainly a description of some changes relative to standard ML. Um, and I view this as an exercise in microdesign language where I'm not touching the core characteristic features of the language. I'm not trying to introduce, for instance, a new paradigm into the language. And it's important to note that I'm not concerned with backward compatibility. I want to treat this as a quasi clean sheet design. Okay. So why am I doing this? Well, I started a project a while ago to basically rewrite most of the front end of the standard ML of New Jersey compiler. This was a personal project because I was fed up with uh, various aspects of the fairly ancient implementation that started back in the 1980s. Um, Also, I had a bit of nostalgia for the good old days of language design. If you got into this field in the beginning, around 1975 or even earlier, there was a lot of open ground and a lot of discussion of language design that ended up led to the design of standard ML over a period of years at Edinburgh. And there are a couple things which could be called settling old scores, fixing old mistakes. Certain mistakes in language design became evident to me and a few others. And we had a chance in 1995 to 1997 to work on a revision of the language, but there were certain constraints on how that came out. And so certain things that some of us would have done were not done. And so this was to some extent a chance to correct that. Okay. So I want to just remind ourselves of the basic character of standard ML. I put parentheses around the capital S in standard ML or SML because standard was a kind of a mistake as an adjective describing uh, the language. At the time that Robin wrote the original 1983 kind of core language proposal, he termed it standard ML, which was an attempt to unify various branches the original LCFML, a slightly modified version that came to be part of Cambridge ML, done by Larry Paulson and Guy Cousineau, and the ideas from the Hope language that Rod Burstall and I had worked on at Edinburgh. So the computational model that should all be well known is strict lambda calculus, strict functional language. It's statically typed. The type system is basically the core of the type system is basically Church's Simple Theory of Types from 1940. It has a few major innovative features such as parametric polymorphism, automatic type inference, and algebraic data types, which came from the Hope language. And it also, of course, has a functional style module language. It has simple modules or structures. They have types which are called signatures, and then functions over those. Originally first order, later on, and in this proposal, higher order. Okay, it's useful to think of how ML is designed versus Haskell. These are the two main versions of functional programming in the world these days. Obviously, purity distinguishes them. ML is impure and Haskell purports to be pure. The evaluation order, strict versus lazy. Interpreted types, that is, types together with interfaces of operations and values, are represented using modules and functors in ML, and the implicit propagation via type inference in Haskell. So the ML has a formal definition, which was it's a first order goal of the whole effort. And as far as I know, there's not a formal definition of Haskell. Some major changes. The bold ones I'll come back to and discuss a little bit more later on. Deletion of the open declaration, and which seemed like a good idea when we were doing the original language design, that turned out to be problematical. So we can do without it. I also wanted to delete equality polymorphism, the associated equality type variables represented with a hyphen hyphen, like hyphen hyphen A for alpha. Delete, going along with deleting open declarations, I would delete the include specifications in signatures, and also the module system should have the higher order functor feature that was introduced in SMLNJ 0.93 back in, which was released in February 1993. So we have a fair amount of experience with the higher order functors over the years, although they're not supported, they're not in the definition book, and therefore they're not implemented elsewhere. Some more major changes, mostly in the core language. One is that type variables that appear in expressions and expression level declarations should have a binding. And the infix declaration feature was something that was in the Edinburgh culture because of POP2, but it was a mistake to include it in standard ML. And it's also something that I've been thinking for a long time, which is that one shouldn't declare types within expressions, say in the left part of the declaration part of a left expression. And this is a bit controversial because some people are strongly in favor of this, but it kind of tends toward flattening the module and core languages. And in my opinion, that's a mistake. Another kind of convenience feature that's been missing, and people have wanted this forever, which is the ability to kind of do functional updates of records. And the simple general way of doing that is to have a kind of overlay operation on records. And so the abs type and while expressions go back to the early days and are sort of carryovers to some extent. And abs type has been superseded by having um, structures with opaque or abstract signatures, and while expressions are usually done by fold or some recursive function. So back to the open declarations. One problem is that if you use them too enthusiastically, you introduce too many names into your local namespace, and it becomes difficult to figure out where the names came from. The other problem is that open creates a serious problem for doing static dependency analysis between modules, which is, of course, an interesting analysis to do for purposes of such, for instance, the compilation manager CM does this kind of analysis. So here's the old style. We actually had modules that looked a bit like this, where we open up everything that is needed, just throw all these names into the current namespace, and then you use one of them, like name, and you don't know which of those 17 structures the name came from. And of course, name might be exported by multiple structures, and it just, you get whichever is the last one that was opened. And that's messy and bad software engineering, if you like. And the workaround for this that we've come to adopt informally is basically to, instead of opening structures, we give them short local abbreviations like S for symbol, et cetera, et cetera. And then in the body of the structure, in the scope of these declarations, we can then use t.name to indicate the name variable coming from the structure T, abbreviated to T, in this case, types. Okay, deleting equality polymorphism. Languages tend to have some kind of generic equality. And in the past, Lisp, pop2, whatever, often in dynamic languages, but even in static languages, like Hope, one of the precursors of standard ML. So you start with certain primitive types that have their own primitive equality, say integer. And you can propagate equality for constructs like products and sums. You can inductively define an equality over a data type, such as lists. And the basic principle is that function types are not equal, do not support equality, and abstract types do not support equality, although you can define an equality operation for a given abstract type. And this means, of course, that you need to explicitly pass the appropriate equality for abstract types as part of your parameter set. So it's a little work in that sense, but equality types introduced what was essentially a type class into ML, and we don't want to adopt the type class mechanism in general, so let's get rid of this particular special case. So the problem of explicit type variable bindings, the principle is that any variable used should be properly and explicitly bound somewhere in code. So we can write a function f of x equals, and then we can refer to some type variable alpha somewhere in the middle of the definition of f. And then the question is, what is the scope of the implicit binding of alpha? And if f is one of a family of mutually recursive functions, that can get a bit complicated. Sometimes we might mention alpha in the typing of the function parameters, which tends to suggest that it might be local to this function, but it doesn't really do that. And in SML'97, we introduced a syntax for binding type variables in association with declarations like function declarations. But what I'm suggesting for MsML is that we have some kind of binding construct, and this syntax is throughout this discussion, syntax is all hypothetical. And so my suggestion here is that capital X will be a type variable, and this square bracket notation binds it, and then it can be referred to in its scope, which includes both the parameter types and the body of the definition of the function. Anyway, that's a kind of cleanup that's long overdue. There is an algorithm for inferring the binding site of type variables that appear randomly in an expression, but that algorithm is non-obvious. And everything should be obvious to people who are very familiar with the language. If you have features for whom even experts find things a little bit puzzling, that's bad. And I've always found this algorithm annoying and puzzling. Okay, so this convenience feature, this is one of the few additions. It's always been desirable to have a functional notation for updating a record field. And so the simple way, in my opinion, is to just allow kind of overlay, like overlaying an environment. A record is like an environment. It's a mapping between field names and their values. And in historically, several times, the with word keyword has been introduced and used as a record overlay operator. And we can't actually, this is strict in the sense that it's assumed that you're operating on record values, but it can't be defined as a function or operator because we have no way of expressing the type in general. And you might think about trying to express the type using row variables, kind of polymorphic type variables that range over parts of records, but that turns out to be kind of messy. So if we are going to come up with a new version of ML, a successor ML, there are a couple things that one ultimately takes an obligation to do. One is that there should be a formal definition of this new dialect. And there's a question about should we just edit the old definition, which is in a rather archaic formalism from the mid-1980s, or should we choose a new definition, formalized, hopefully mechanized? For instance, Bob Harper and Carl Prairie implemented a definition of standard ML in the 12th logical framework, or theorem checker. The second obligation is that if you are going to have users of such a new language, you have to reconstitute the whole software infrastructure, the compiler, libraries, tools, and modify their code so that they compile in the new dialect. So that's a lot of work. Although after the SML'97 revision, it really didn't take that much effort to adapt rather to the changes that were made then. So it's routine, possibly partially mechanizable. Okay, to summarize, So MsML is a variant of standard ML, a successor ML, but it's mainly preserving its uh, core character. In my opinion, nothing essential is thrown out. The things that are thrown out are not essential, and very little is added. And that's a little bit vague because in the course of filling in the details, there will probably be additional additions. The module system is one area of the design which deserves a little bit deeper rethink, I think, than the core, because there's been in the intervening decades interesting research done on the module system by Harper and his students and other people at Carnegie Mellon, and by people like Claudio Russo and Andreas Rosberg. So, there, as I said, there's the issue of if this is going to be formally defined, what formalism should be used, and of course, then who will do it. And the project is associated with my planned work of reworking, rewriting the front end of the current SMLNJ compiler. And I'll go back, and the resources at this point are that there's a text file, proposal/language.txt, in this GitHub repository, new front end in my GitHub project. And there's a chat locale venue called standardml.zulipchat.com. And there's a channel on the topic of successor ML within that discussion group. That's analogous to a Discord. There's actually a standard ML Discord group, but I, for various reasons, prefer Zulip chat, or Zulip. And if anybody wants to kibitz about this, they can contact me at my email address, dmcqueen@mac.com. And that's more or less it. If hopefully there's a bit of time left for questions. Are there questions?
Yes, thank you, Dave. Fun talk. Do we have questions? We do have some time. Sam.
Hey, Dave. This is Sam Westrick. So you mentioned one of
Okay.
your ideas was to not worry too much about backwards compatibility, but also the language that you've outlined here, I mean, it's very similar to standard ML in many ways. So it seems like there's an opportunity to get the best of both worlds. I mean, you're working on a new front end. Maybe the new front end can actually automatically migrate SML code to MsML code in many, many cases. And anyway, I'm just kind of curious to hear your thoughts on the feasibility of that.
Right. There are certain things that could be automated plausibly. And we thought about this with respect to SML'97 versus SML'90, the original published definition. And in that case, it turned out to be not too hard to do it manually, so nobody ever got motivated to try to write a software tool to translate from SML'90 to 97. And it wouldn't have been entirely trivial anyway. There's also the idea of a tool that would translate, say, OCaml code to standard ML and vice versa. That was a big damaging fork in the whole history of the language. And there's a question about should deeper changes be involved? And we went through an exercise called ML'2000 in the 1990s, from about 1992 until early 2000s. And that involved a lot of people, both from the standard ML community and from the OCaml community and others. And it didn't work mainly because there wasn't sufficient consensus, and mainly on the issue of whether object-oriented features should be introduced into standard ML. Yeah, whenever you start loosening things up by considering changes to a language, there are many changes that could be proposed. And in the previous discussions of successor ML, there are quite a long list of proposed changes, most of them quite small. And there are things like recursive modules, which have been fairly deeply explored, but they don't seem to be um, uh, obvious enough. So I have a personal criterion, and it was that whatever feature you introduced into the language should be obvious to a uh, practitioner using the language, somebody who's quite familiar with the language. And of course, obviousness is a subjective thing, but there are certain things that I regard as non-obvious, like um, GDTs, generalized data types. I've always considered those quite non-obvious. In the object-oriented world, the notion of inheritance and control flow associated with inheritance and all that is quite non-obvious. And therefore, I would like to have it in the language I designed. So that's roughly the answer. Any other questions?
I have another question.
Hi, I'm Songhon. I'm a new student with Sam, and I'm wondering if some of the, some of the rules like not having open or not having abs type could be implemented at like a linter level and try to apply that linter to something like a large standard ML code base like SMLNJ, and kind of test out the ergonomics of that, whether people actually appreciate these removals, whether people found them actually to be more of a hassle, and then with sort of like after canarying these removals, then maybe we can make a better informed decision about whether these features actually, having these features actually leads to more confusion rather than added utility.
That's a very interesting and plausible proposal. One could easily um, have a flag in a compiler that would issue a warning or even an error message if you used open, for instance, and that would quickly expose where people were using open. And if it's just a warning, they could ignore the warning. And for certain things, that's plausible. For other things, I'm not so sure that would work. For instance, with the explicit binding of type variables within expressions and declarations, one might modify the current inference mechanism to actually insert binding constructs into the code. So these are interesting and plausible, but again, somebody has to do them.
Okay, thanks very much, Dave. I think we, in the interest of time, need to move on to the next speaker, but this was a fun talk, and I
Okay.
want to thank Dave again.